Hello everyone, welcome to the 13th lecture of Electronic Devices and Circuits 2 course. We have discussed quite a bit about the filter circuits so far. We have learned how to construct the different filter circuits, low pass, high pass, band stop, how to derive their transfer function, the cutoff frequencies, and also how to plot the frequency response plot using the Bode technique. So we have learned quite a bit. So now the focus of this lecture is how we can get higher order filters. So first we will define what is higher order filter and how the order of the filters are defined and what are the merits of higher order filter circuits, and then we'll discuss how we can realize the higher order filter circuits. So we start with our well-known Bode plot for the low pass filter. As we know that the Bode plot of the low pass filter is made of two straight lines. One is the 0 dB line that is below the cutoff frequency omega c, and the other is the slanted line with a slope of minus 20 decibel per decade. So this filter, which has a slope of minus 20 decibel per decade, that means that the gain falls at the rate of 20 decibel per decade. Every 10 times increase in frequency, gain falls by 20 decibel. So this type of filter is also known as the first order filter. So in the bracket it is written as first order. So the filters that we have discussed so far, all the filters are actually first order filters. The low pass, high pass, band stop. If you remember that when you drew the Bode plot for the different filters, we got the slope 20 decibel per decade. For all the filters, the slope was 20 decibel per decade, indicating that the gain is falling at the rate of 20 decibel per decade. So for the filters where the gain falls at the rate of 20 decibel per decade are also called the first order filters. So the filter circuits that we have discussed so far all belong to the first order filter. Now what are the higher order filters? The higher order filters, the gain falls at a higher rate. The higher is the order of the filter, the higher is the rate of fall. Like this is the first order filter. If it is a second order filter, the rate of fall will be twice as much. It will be 40 decibel per decade. If it is a third order filter, the rate of fall will be 3 times. That means it will fall at the rate of 60 decibel per decade. If it is a fourth order filter, the gain will fall at the rate of 4 times of this rate. That means it will fall at the rate of 80 decibel per decade. This is how for increase in every order of the filter circuit, rate of fall will increase by 20 decibel. So let's see how the plots will look like. So this is for the second order filter. Gain is falling at the rate of 40 decibel per decade. As you can see, at 10 omega c, gain is 40 decibel minus 40. This is the third order filter. At 10 omega c, gain fell to 60 decibel minus 60 decibel. The fourth order filter is falling at the rate of 80 decibel per decade. So the higher is the order of the filter, the faster is the rate of fall. The gain falls at a faster rate for higher order filters. And then you see that this dashed line here, which shows a steep fall in gain. So that is for ideal filter, abrupt or sudden fall in gain. So ideal filter, there is a abrupt transition from pass band to stop band. Stop band, the gain is 0, so it will fall sharply, abruptly. But practical filters, gain falls at a steady rate, at a constant rate. And the higher is the order, the faster is the rate of fall. So what happens? The higher is the order, the faster is the rate of fall, and the closer it will get to that of the ideal filter. So from this we can say that higher order filter will their characteristics will be closer to that of the ideal filter, and the higher is the order, the closer it will get to that of an ideal filter. So what are the merits of a higher order filter? Filter characteristics, as we have said, is more closer to that of an ideal filter. The higher is the order of the filter, the faster is the rate of fall, and the more closer the filter characteristics gets to that of an ideal filter. So the benefit is that ideal filter will allow only the signals that we are supposed to pass through and completely eliminate the unwanted signal. In the stop band, it will remove all the signal, 100% it will block. But practical filter cannot block 100%. Even in the pass band, there will be some transmission. But the higher is the order of the filter, the more effective it will be in filtering action. The more it will be able to block the signals, and the output will be more accurate. You will get more precise output with the higher order filter. So that is the benefit of higher order filters. The filter becomes more effective in blocking the unwanted signal, and the ultimate result of more precise and less noisy output. So what are the demerits of a higher order filter? Are there any demerits? Yes, there are demerits. The higher is the order of the filter, the more circuit components you will need. So the bigger circuit will get bigger. It will consume more power. It will occupy more space, and it will cost more. So these are the price you have to pay at the end of the day to get a higher order filter that will perform better. So it comes with a price. It's not free. You get an improvement in performance of the filter circuit by increasing the order of the filter, but that does not come free. You have to pay for better performance. So now we'll see how to construct higher order filter circuits. Now that you have learned what is higher order filters and what are the merits, what are the benefits. So definitely we need to know how we can construct higher order filters so that we can get those benefits in our filter circuits. So here you see that in this diagram uh, we have two first order low pass filters. This is a low pass filter, and this is also a first order low pass filters, and two first order low pass filters, they are connected in series. So when you connect two first order low pass filter, the result is a second order low pass filter. Why it is a second order low pass filter? How do you know that it is a second order? The definition of second order low pass filter or second order filter is that the gain should fall at the rate of 40 decibel per decade. Now, does it fall at the rate of 40 decibel per decade? Yes, it does. Why? How? Because this is the first order filter. Here the gain will fall 20 decibel for every decade increase in frequency. Then this is another first order filter, and here also gain will fall another 20 decibel for every decade increase in frequency. So each of these filters individually, they will provide a fall of gain of 20 decibel per decade increase in frequency, giving resulting in overall decrease in gain of 40 decibel per decade increase in frequency. So this is how, by joining two first order filters in series, you get a second order filter. We have joined two low pass filters in series, and that will give us a second order low pass filter. Now the circuit below, you see that there are many op amps, many filter circuits. So the first two are the first order low pass filters that will give us a second order low pass filters. And then we have this one is a high pass, first order high pass filter, and that is joined with another first order high pass filters. So we have two first order high pass filters connected in series, giving us a second order high pass filter. So we have a second order low pass filter that is connected with another second order high pass filter. So that will make it a band pass filter. And then finally we have a gain stage. So we have here basically a second order band pass filter, because why it is second order? Well, we have a second order low pass filter that will give us a fall of gain of 40 decibel per decade at the high frequency end, and then we have the second order high pass filter that will give us also 40 decibel per decade, that will give us a fall of gain of 40 decibel per decade at the low frequency end. So both at the high frequency end and at the low frequency end will get a fall of gain of 40 decibel per decade, resulting in a second order band pass filter by definition. So this is how we can construct a higher order filter by joining more number of first order filters in series. The more is the number of filters, the higher will be the order of the filter. So you can easily see that for higher order filter we need more circuit components, it will consume more power, it will occupy more space, and of course the price will go higher and higher the higher is the order of the filter. Now there were two scientists, Salen and Key. They developed a filter circuit, a second order filter circuit, by using just only one single op amp. So this is a second order filter circuit, and that uses only one single op amp. But here the gain falls at the rate of 40 decibel per decade. If you derive the transfer function, do the Bode plot, you will see that the gain here falls at the 40 decibel per decade. One of the feature of the second order filter circuit is that it should have two capacitive element of two reactive elements. A first order filter circuit will have only one capacitor. Second order filter circuit should have two capacitors. Third order should have three capacitors, and so on. So the number of capacitors also goes up with the number. So what are the merits of the Salen and Key filters? Salen and Key filters use only one op amp to construct a second order filter, unlike we have seen that we need two first order filters with two op amps to construct a second order filter in our previous slide. And so it occupies it takes less circuit component, only one op amp instead of two. It will consume less power and it will occupy less space. It will be cheaper. So these are the merits of silent and key filters. And so this is our second order low pass, and the counterpart of this one is this one, the second order high pass filter, that we can easily get if you just swap the resistors with the capacitors, the position of the resistors and the capacitors, you get the high pass filter. So this is our second order silent and key silent and key high pass filter, and this is our second order silent and key low pass filter.